Hi, we are Group 15. The topic of our final project is traditional and deep learning-based lane detection. Start with why we want to study lane detection. Lane detection is one of the critical elements that ensure the proper function of autonomous vehicles. With the fast development of computer vision, cameras have become increasingly important for assisting autonomous driving due to its high accuracy and relatively low cost. However, the images recorded by cameras cannot be used directly unless we apply lane detection algorithm to extract the useful information. Therefore, in this project, we investigate and implement several lane detection algorithms. Two are traditional methods by using canny edge detection or sliding window algorithm to detect straight and curved lanes. And another method is a deep learning model called PyNet, which consists of several stacked hourglass modules. The dataset we use is a too simple dataset. We have detailed information about it in the next few slides. Too simple dataset is very large. 11 gigabytes training images and 11 gigabytes testing image totals 7,000 1-second long video clips of 20 frames each. Our goal is to take the images in, detect the lane for each frame, and concatenate them into a video. Here are two sample images from the dataset. We can see the weather is great, the light is pretty good. Though we might have some cars on the road, the complexity of this dataset is not too high. The number of lanes is not fixed. We might have 2 lanes, 3 lanes, 4 lanes, or more highway roads. They also provide a ground truth label for the training data, which is great for supervised deep learning methods. For the straight lane detection, we implemented the canny edge detection we learned in class. Then we cropped the images to only focus on the roads right in front of the car. Afterwards, we used the TOF transform to find the lines in the images and then use linear regression to get the final results. From this 2 seconds video, we can see that the straight lane detection works great for this simple scenario. However, for an extreme case like this, the car is changing lanes with an highway exit on the right. The straight lane detection cannot figure out which is the correct left and right boundaries. Here are another 2 examples of failure cases. If we have multiple lines or shadows on the ground, the straight lane detection cannot work properly.
The straight line detection can provide reasonable results for simple scenarios. However, in the real world, roads are usually curved and straight lane detection cannot produce satisfactory results for those cases. Therefore, we introduced the curved lane detection algorithm to conquer this limitation. First, we convert the original image to the bird's eye view. Then, we use Sobel filtering to get the binary edge map. We applied sliding window search to remove the noise and detect lanes. Finally, we used second-order polynomials to fit the lane and convert it back to the original view. These 2 images show the intermediate steps of the Sobel filtering and sliding window search. The white color represents edges, red boxes represent sliding windows, and the green lines represent the fitted polynomial in the bird's eye view. In the samples result here, the blue area is a detected lane that the car is currently driving in. From this video, we can see that the curved lane detection algorithm works better in these curved lane scenarios. However, there are also 3 examples that the curved lane detection is not good at. On the left, the car is changing lanes. In the middle, the right line is not clear. And on the right, the spaces between left dashed lines are too large.
PyNet stands for Point Instance Network. It takes input and it resizes to a smaller image. Then the compressed input is fed into 4 hourglass modules. 4 output branches are applied following each hourglass module. They compute confidence, offset, and feature. Then the 3 values are used to calculate the loss. This model takes images as input and ground truth labels as output. This video shows the output of the PyNet. It detects multiple lanes in the image. As a comparison to the curved line detection, from the left image, we notice that curved line detection cannot handle the situation where the car is changing lanes. The result of PyNet is not perfect, but much better than the curved lane detection. Since PyNet can be clipped and transferred without additional training, we trained the model with 4 hourglass blocks and tested the transferred model with 1, 2, 3, and 4 hourglass blocks. The 4 models all produced acceptable results. And the model with 3 hourglass got the best result, which shows the clipping and transfer learning can not only save space, but also improve the performance. In this project, we found the traditional method have several disadvantages, which can be conquered by using deep learning methods. In the future, we can try different deep learning methods and figure out whether they can produce better results. Moreover, we can implement vision-based control. Instead of only detecting lens in the image, we can control the car based on vision and realize autonomous driving. 5分25秒。
Great.